I'm Travis Porter. I've been with the company about 18 years now. So I've seen quite a bit. I've held several positions within the company. Started out in production, and then I went through a series of different rankings on the technical side, and now I'm working the sales side. Um, I've got a lot of experience of seeing what shouldn't be done over the years. So we'll just, move through this on some of these more common methods for calibrating an RTD today. Let me do our next screen. Oops, that doesn't look like it's liking me. Yep, yep. All right. So we're going to do a quick overview of calibrating an RTD using a dryblock calibrator. Go through a quick dryblock introduction, kind of review some of the more common source of error and error problems that you may run into. I do have a slide on kind of calculating uncertainties. We're not going to do any deep dive on that today, but again, just more kind of quick overview of a couple of methods. And then again, different concerns, liquid and glass thermometers, and then dry block maintenance is just some of the ones we'll be going through. So I hope to give you kind of a good overview. Again, if there are additional up as going through the seminar, again, please text those to Steve, and we'll try to address them at the end here. All right, so quick introduction to a dry block. So again, it implies what the title says. It's a well-designed or a heat source designed to be used without any fluids or liquids. So again, hence the term dry. Some of them have fairly moderate accuracy, and then they do have a variety of different block designs. Most of the blocks designs typically have some fixed holes, and then some that are variable. Some have different inserts that are removable. So again, there be some variation between them. Typically, though, in a dry well, depending upon your unit, your immersion depth is going to be definitely fixed depending upon the design. Very portable. One of the other things that people tend to lean towards for a dry well is they're fairly rapid to go up and down in temperature, and that they do have a internal reference probe that does control the display accuracy, so you can get fairly decent display accuracy when you're calibrating, say, thermocouples or gauges that don't require a whole lot of precision. Sources of error that you're going to find when using a dry well is immersion, and that kind of revolve around your probe or your UUT. There's also ones you want to be concerned about as stem conduction, contact errors, and that again usually is referencing the size of your probe to the size of the well hole. So again, there we'll touch on that a little bit further in more detail. And display accuracy, that's the biggest one. So again, the display accuracy of the wells do vary from unit to unit. Another one that you would want to be concerned with is usually the stability of the dry well. And then on some more newer models or more advanced, they do have a radial and axial uniformity spec. We'll also touch on loading and how that can kind of play into potential source of error as well. So we'll touch on the immersion depth, and it's critical. So in my wells, the display sensor is buried down in the bottom of the well. And in this example, you can see here we're kind of showing, a unit being tested in a well, and kind of where the control sensor is of the versus the UUT sensor. And you can see the control sensor of the block is fixed. And so the idea is to kind of line these as close as you can to each other. So when you're using the transfer or the display accuracy of the well, there's not going to be any discrepancies. So again, method here that you're seeing as well can be used, or this is typically how it's used to calibrate the well. So if having a UUT, you're going to use a higher sensor and align those closely for the calibration of the well with a much higher accuracy reference probe. So again, it goes both ways with those. Just depends on where your reference lines up as far as uncertainty. All right. Now we're going to touch on immersion effects. Again, immersion usually to do with, again, the sensor itself. Alarms, depending upon the makeup of the sensor, sensor lengths and diameters vary in the UUTs. And then also the outer sheathing. These things kind of play into immersion depth for a probe. Again, a good rule of thumb, I've heard a couple, and on this particular side we've got 15 times the probe diameter. Other rules of thumb I've heard are 15 times the probe diameter plus the length of the sensor. That one's fairly problematic in that most of the time folks don't know what the internal sensor make is. And then the kind of the other one that errs more so on the conservative side is just a straight up 20 times the diameter of the cell. So again, typically if if you have say a 1/4 inch probe and you go with one of these rule of thumbs, you end up typically with a 6 inch minimal immersion to kind of negate any errors from that. So another way to kind of negate some immersion effects in the example here is to use a reference probe as well versus a straight display accuracy. This can immerse the UT and the reference, the block, and kind of use the transfer there, knowing that you're in a very uniform area of the unit. To touch on stem conduction, basically it's where your probe begins to act like a heat sink, so it's going to pull heat in or out of the well. So again, the rule of thumb is a good one to follow. Again, the 15 times the probe diameter plus the length of the sensor can be problematic if you don't know the UUT's sensor. So again, another one that's fairly common is the 20 the diameter. But if you were to get very serious about the stem conduction, you can run a test where you just watch your probe or resin and continually inserting it about a ½ inch at a time until the readings become stable in the heat source. But again, for most dry blocks, the best method again is full immersion. And again, just be wary of the length diameter. Another when using a dry well is the contact between the well itself or heat source and your unit that you're testing. So again, a dry well is basically a contact calibration. The fit becomes very important in that when you get a probe that is in a hole that's too large, you're going to get an air gap, which will cause typically low readings because it's going to be an insulation type effect. And then also if you get a hole that's snug and then you run it up, there's potential that you will get the probe or the unit under test stuck in the well. Typically, for most of dry wells, we do take this into consideration, and we do have a kind of a on the drill sizes. Most of the time, we try to go about 100th bigger than the size of the probe tested. So an example of this would be for a 1/4 inch probe, we typically would drill the hole at like a 0.65 to allow for good thermal contact, but also enough room to allow for thermal expansion. So, display accuracy of the dry well. Typically, most manufacturers will say a 1-year spec when putting these together. Instead, it's always recommended that you do have some sort of internal QA program. Again, things can change with time and also handling. So, again, a good practice to put some sort of a QA process in place to where you don't kind of send it off for recertification and then discover at that time you've had an issue that you were not aware of. Internal sensors of the drywalls are designed to be robust and have a low drift. Things to be aware of there, especially with a drywall. You got to be again, they are still typically an RTD type sensor, and they do or actually do not respond well to physical shock. So if you're shipping the units around or if they're a field unit, handling typically does come into play, regarding the accuracy or drift of the sensor. The other thing that I've seen cause problems is when you're removing and inserting the wells or inserts of the unit. You want to set these in gently and avoid, just getting, it partially in and then allowing it to drop. That will or can cause a physical shock to the sensor. It's also recommended that if you're shipping them, that you remove all the inserts from the wells before shipping them out. Because again, if it's down there and is bouncing around during shipping, it can cause physical shock to that itself. When you're looking at drywalls, please be wary of the display accuracy, because again, that's typically one of the more the larger uncertainties of a drywall. So again, I hope that touches on some of the display concerns there. Other one, when you're shopping or considering a dry block, is the stability specification. Typically, most manufacturers, including Fluke, on a dry well, we do optimize the banding for the stability of the unit to work across the full advertised range of the unit. So if it's say a 50 to 400 degree C unit, we do testing to get stability across that range. Some folks will fine-tune proportional band. On most of our drywalls, it's not recommended. That fine-tuning of proportional band kind of comes more so from folks using a large calibration baths where you've got different considerations around the fluid and viscosity, different things there where you can make an adjustment. Where the things in a dry well, such as the blocks and the insert, are fairly consistent. There's no other considerations. That's how we can optimize it. So most should be fairly optimized, and again, it's typically not recommended that you try to tweak the proportional band. And if you do stability issue in your unit and you think it's more likely, I would say something wrong with the unit, not so much a proportional band error. But again, that's something to consider and look at first. Consideration of a dry well is the axial uniformity, or top to bottom. A lot to kind of be said there, depending upon the makeup of the unit. Typically, heated units with heaters have a much larger axial uniformity versus some of the other units that may use Peltier devices or other devices. But also, the heater design itself plays into this. So again, when you're using a dry, again, in this particular example, we're kind of showing a worst case of a very short sensor where we have very poor emission, and then we've got the control sensor down there at the bottom. Most we call WC drywalls, we're very concerned with an axial uniformity spec. On some of our newer, what we call metrology wells, we have kind of dug in on this particular specification. So if you notice down at the bottom of the slide, we have specification, I believe, is taken from one of our metrology wells. And so you'll see actual uniformity at 40 millimeters or 1.6 inches. So what this means there's, not at that particular point, but it's referencing full immersion up 1.6 inches is we're going to have a good zone of plus or minus 0.05. Things to consider in your applications. Again, especially if you've got a lot of short to be tested. All right. The next to consider is radial uniformity. This is also known as hole-to-hole. In most well designs, you're going to have a variety of holes. Some are fixed within the block, and some are variables within the insert. And depending upon the dry block design, these are going to vary. Most OEMs do have a spec for radial or hole-to-hole uniformity, and again, this means if I'm in the example here, if I'm placing a similar size probe at, say in this example, at 1 o'clock, and then I place the opposing unit at 7 o'clock, we're going to have a potential of a 0.10 C discrepancy just from the placement. A lot of this is researched and tested very well in the R&D process of a dry well, but something to be another consideration is loading. So it can impact uncertainties because, again, depending upon the well design itself, I've seen some folks that will take a fairly small well and then try to calibrate a fairly large sensor. Sometimes, basically, the sensor size, the most of it is just more than the well itself is designed to handle. So again, an example would be if we had one of our handheld dry wells. We do have a model with a half-inch hole design, but I would not recommend, say, a high temp half-inch by 12-inch unit and mate that with that as a good solution. But the mass of the probe or unit under test is going to basically outdo the design of that well. So sometimes you can get more basically units with a little more horsepower in the realm of the heater designs and setup, and that can help with that. In our new again metrology wells that we've designed when we came out with them, we take these into consideration. So we do try to provide kind of an idea of a loading effect. So in the example at the bottom of the page, this is a loading effect with a reference probe and 3 units on the test of sensor size. You're going to see a discrepancy there of potentially 6 millik. So again, really small on the loading, but it is a consideration, especially if you're doing large quantities of units or the physical size of the actual sensor is large, and the temperature range is also something that can play, especially if you're going to the extreme hot or cold with a fairly large size unit under test. So again, that loading effect spec again here that we're providing is just to give you an idea of what to expect potentially when running the unit. All right, now we're going to jump into a couple of calculating uncertainties. We're going to go through two and it's kind of we're going to do the higher level and then kind of the deeper dive. We're not into in this particular one how to come up with the coefficient, but more or less just show kind of the certainty of the reference and heat source. This one here that we're looking at now, or the root sum squared method, basically is just taking into account our reference and the accuracy specification, but even in that piece, usually there's its own set of kind of a breakout to get the certainty for the reference. Usually it consists of the uncertainty and then a spec on the reference probe itself. Beyond that, typically you will take the stability and uniformity of the well and build that into your equation. Now, if you're calibrating directly to the display of the itself, in this particular example, you would negate that reference that we're showing as an external and then simply build in your display accuracy. So again, that kind of gives you an example of how to put together a quick uncertainty analysis for a well with a reference. And move to the next one, where some folks jump up to what we'll say like an accreditation or a 17025 or one of these higher compliance type examples. You really have to break down the uncertainty. And in here you can see that they've kind of broken it out by some pretty common ITS 90 test points, which is mercury, typically the triple point of water, or 0, tin, zinc, and aluminum, going left to right. And you can see that they've broken down their UUT, reference, calibration, probe drift, axial and radial uniformity, and again, insulation, repeatability. So again, a much deeper dive in what they're looking for in an uncertainty. But you'll also notice here, not just using a plus minus uncertainty, they're actually breaking it down into a K equals 2 of all of the various pieces. And so the K equals 2 is more or less a 95% confidence that if I make a measurement at, say, 0, I'm going to have an uncertainty. And in this case, I think most folks will work in the milli K, so it's not 21, it's like 0.021 milli K, or you're equating that C, a plus minus 0.021 C uncertainty for that particular temperature using this setup here. From today, find yourself trying to use a drywall with some off-shape probes. We do sell basically blanks and custom drilled that do work, but again, there are the considerations of these probes that if they are, extremely short, or the mass of them is kind of outside what we would expect, the best option, especially for shorter, higher temp probes. Usually those options or situations we'll discuss moving from a drill type application to a bath or micro bath or something that may be more appropriate, that will get you a better unit stability versus trying to calculate it using a drywall. But again, with a drywall, we do have options, whereas variety of inserts, and then also the ability to design custom or inserts that are unique or specific to particular applications. I'm going to touch on basically temperature concerns. So again, a lot of times you'll need to calibrate over a range of temperatures. Unfortunately, the technology exists where we can get typically extremely cold to extremely hot within a single unit. So most products, have a variety of range. Typically, you'll get the series of cold wells and kind of a moderate well, and then your very hot wells. And it's okay in a process if you have to switch from one well to the next. Again, you would just have to kind of reevaluate the uncertainties of each well, and then consider that with either your reference or the display accuracy. So in these examples here, we're going to show the Fluke products where we have the ability basically to get as cold as 95 C and to 1200 C across a variety of different wells. So again, depending upon application, we usually have a product that will fit the need, but there are some considerations as far as going from an extremely cold temperature to extremely hot, just because the technology does not exist to kind of make that happen in a single unit. Another common thing that comes up with drywalls is, as people will say, well, can I calibrate my liquid and gloss in them? I have some people do it. It is not recommended. The reason for that is mercury thermometers do have a bulb at the end that is the point of contact, and that bulb usually varies in shape versus the stem. So basically, if you get a hole large enough to accommodate the stem, your bulb has usually got a nice air gap around it, which results in low readings. That said, depending upon the accuracy of the lig, it may or may not be a concern. But again, typically over the several years now, mercury thermometers are kind of becoming less and less common. They're kind of on their way out due to the environmental concerns. One thing to consider that we've kind of come to the market with to kind of replace those is kind of our stick thermometer, where again we kind of went at the particular lig market there to kind of have an alternate electronic RTD solution. So again, something to be aware of as far as calibrating ligs in a drywall. You typically don't get super good results just due to the bulb getting a nice air gap, later insulation effect around it in the well. Drywalls, we're going to touch on the maintenance now. They have metal blocks. Typically, they're usually some sort of brass or aluminum type block material. For these types of units that have these types of blocks or inserts, metals oxidize. Even if you're not using over extreme temperatures, even on the cold ones, you will get some condensation out of the air. So again, you get some basically some like on your kitchen sink where you get these little small micro buildups. A good way to clean those off is spray. Again, just give your inserts a good kind of going over. I mean, some that have gotten really aged over the years, and you can get a little more aggressive with those if they are giving you some trouble. Usually, I would recommend like a 400 to 600 grit sandpaper and kind of clean them up there. But again, typically a gun cleaning kit with some of those brass brushes works well to keep the wells very, very clean. So again, no tip, don't use thermal grease in a well. I've seen that happen a few times. Basically, if you don't clean it out regularly, it becomes a glue, and then you run the risk of gluing your insert or probe to the unit. And again, just on the maintenance, recalibrate and verify them regularly that you're not overlooking a potential issue in the work that may cause a recall or error potential in your process. All right, I'm going to run through a quick RTD calibration example using our 9190 drywall here. It's one of our units that goes really cold, has a fairly good upper end. What we would do here is we're going to set up the unit, and typically when you're calibrating, you usually go cold to hot. It usually makes for a quicker transition just within the heat source itself versus going hot to cold. We would set our point at the cold point, let it reach temp, allow to kind of slice for 15 minutes or so, and then we would record our, in this sample here, where we've got the reference temperature and then our UUT's outputted resistance. We would write this down. We would then continue to the next point, allow for the same stabilization, note the actual temperature from the reference, and then the output resistance, and then move to our next point. Once we have this data, you can use, in my world, I've always used Tableware, which is one of our coefficient calculation softwares, but some folks will use polynomials or other means to come up with the coefficients needed for the calibration. Here's just a quick example. If we were to take that data and then input it into the tableware, again here, looks like our reference temperatures were perfect, and then we've got our output resistance temperature, and then you hit calculate, and it will spit out a looks like a calendar Van Neusen coefficient for us based on this input. And we have some additional tool accessories that can be used in conjunction to help speed up your calibration process or cycles. The thing to kind of touch on around the tools to kind of help improve upon process time or tech time. One of our units that we've come to market with a few years ago have basically built-in drivers now, so it can be used not only as a reference but also kind of a stack or a input model for multiple units to collect UUT data as well. And in addition to that, it's got programmability where you can simply set up a table. So in the example before, we could load the unit with a few probes and our reference, and then simply tell it to go to these different test points, and then the unit would collect the data, and then we can extract it via thumb drive off the front panel, and then go back and calculate the code for the units there. So again, just another innovation depending upon what your business entails. But again, we do have tools and accessories to kind of free up more time versus manually waiting at setting set points and waiting for things to happen. So this can free up some of your tech time there. So again, some ideas out there on how to improve using a drywall as far as time savings. Also, to have a few application notes and videos on our web. It just doesn't pertain to drywalls. It kind of spans all of our products. So I would encourage you to kind of go out there and snoop around and see if there's anything that can be helpful to you. And again, too, we're always glad to take any emails, questions. Again, the Christian business is what we do, and so it's we're always happy to talk shop, even if it's just to kind of bounce ideas off us against a kind of unique application. All right, summary here. Dryblocks are a great option in many situations. Again, they're very portable, very rapid to change in temperature. Again, just be wary of the potential sources of air that should be considered when performing a calibration using a drywall. Again, some of the ways to negate that are some of the onboard references or an external reference. So in the example here, I'm kind of referencing my 9140 series field metrology where we've kind of combined a heat source, a reference, and then inputs for UUTs all into one unit. So again, trying to create time savings and equipment savings by kind of implement into a single unit. Again, be sure to contact us anytime for any specifics that may be unique to your particular application. We can kind of give you our 2 cents, and we're always happy to do that. And again, I encourage you to kind of go back out on our website and look at our variety of different application notes and white papers and different things. Again, we're here to help you and be your number one technical source out there in the calibration world. All right, for now, we're going to start our Q&A session. I think Steve have some additional comments.
Okay, thanks, Travis. We're to start answering questions. I've received a few. If you've thought of other questions, please text those in now through the chat window, and we'll start answering these. The question I got was, had a copy of the presentation slides. I will be sending out an email to everyone who registered. That will include the presentation slides. I'll also include a link to the recording where you can go back and reference that in the future. So our next question here is in your panel, Trav. I'll just read it. The UUT probe is very long, like 2 times the depth of the well, and does it make the uncertainty larger?
This will go back to kind of the analysis on the rule of thumb. More so, the length does put a little bit into it because of the stem conduction air, but it's more the diameter. So I would be curious to know what diameter of your sensor is. Again, typically, if you use that 20 times the diameter of the probe, you're going to be fairly covered as far as stem conduction air. But again, more immersion is always better, but it's not a deal killer as far as performing a calibration.
All right, the next question is, how does Fluke recommend measuring stability to verify drywall stability spec? And is the stability measurement based on standard deviation of the set of measurements or the difference minimum maximum?
So on the stability specification, I'm trying to remember now back from my tech days. I do believe we specified, I think if you get the fine print, our stability specs are based over a 30-minute time period. I think it is once a block has kind of come up and stabilized, it's based on the variation. So once you're at stability, kind of up there, how much it's moving above or below that set point. But again, stability, we do try to do a fairly long ratio in the calibration process where we watch the stability at the different test points for about 30 minutes. Now, that's really long. Most of the time when you're collecting data, you're not going to be measuring samples for more than just a few minutes. So again, the shorter actually improves the uncertainty there for you versus taking data over a long 30-minute period.
Okay. Our next question is, how much is Fluke 9190A? So that's our ultra-cold field measure well that mentioned in the presentation. It goes from minus 95 degrees up to 104, so real cold and up to a good hot range. Depending where you are in the world, I'll just give you the U.S. list price. It's around $16,000 for that. Okay, let's go to the next question. Here it says, I'm going to calibrate probes with an accuracy of 0.3 C, range of minus 25 to 150 degrees. What dry block would you recommend? Also have a Fluke 1523 with a 1516 probe that I would use to measure the temperature if the readout isn't accurate enough.
For that particular range, you're just over what our 9103 would do. I'm thinking that this is where we kind of come up against that technology bump of going cold and hot. On that 150, I'd have to, but I think our 9142 may get the job done, or one of our 9172s. Again, most of our units that go cold typically top out around 125, I want to say, just due to the technology, but I think we have a couple models that will bump beyond that. I do have a micro bath, was kind of an extended range 7103, but again, it's going to just shy on the cold side. I think we've got that spec from minus 20 to 150 C. So again, we're just kind of running up into a particular test point, some of those limitations with the technology used in the drywall, but I'm thinking we have something that gets you close. Depending upon the size of your probes, you could look at our 9009 unit. It's a dual well unit, or our 9011, and that would definitely get you covered, but we're going to be way overshooting what you need on the top end there due to that dual well capability.
Okay, great. Let's try the next question. I don't know if we can answer it, but we'll give it a shot. He's asking about, he'd like information about calibrating process calibrators such as the Fluke 26 or 754. Are you familiar with those, Travis, or do we need to get some other help on that?
I'm familiar with units, but not the Calibrate process or what is needed. The 754 does integrate a few of our different dry wells, but again, they're kind of considered part of our G group. F726 is like a multi, what a multifunction calibrator as well. But they don't typically kind of line up with our metrology products. The 54, I know you can use pieces of the programming there to integrate an RTD as a reference and then drive some of our drywalls with it. But the best resource there would probably be what is on the industrial group. There's Fluke IG technical support, and they're the best people to discuss that with.
Okay. Next question is kind of related to that. We'll try it though. Always had a big difference between block display and the Fluke 726 multifunction calibrator as a reference, especially in high temperatures, about 800 degrees C or more. Any idea what the issue may be there?
Follow-up question for me, or what are you using as the references in an RTD thermocouple, and how hot are we talking here? Again, typically, depending upon a 726, I think they'll read again, I'm just going from memory, like a Class A type probe or maybe a B. But again, as you approach some of those higher temps, the uncertainty, since it's kind of just a generalization of RTD performance and not so much a specific, or a more magnified look at how it looks. As you go up or down, typically from the 0 point, your errors do increase significantly. I would need a little more part as far as what's being used, how it's being used, and what heat source is, and different things to kind of make a better analysis.